The conductors that leave the secondary side of a transformer are considered secondary conductors or service conductors because they receive their supply from a derived system. A derived system is a system that receives its electrical supply from another electrical system, typically a primary distribution system. The conductors that leave the secondary side of a transformer are connected to the load, which is the equipment or devices that use the electricity. Tap conductors are conductors that are connected to a transformer to provide power to specific loads. Tap conductors are typically connected to the secondary side of a transformer, but they can also be connected to the primary side of a transformer. Tap conductors are used to provide power to loads that require different voltages or currents than the main load. In the case of a transformer, the conductors that leave the secondary side of the transformer are not tap conductors because they are not used to provide power to specific loads. The conductors that leave the secondary side of a transformer are used to provide power to the load, which is the equipment or devices that use the electricity. To further clarify, let's delve into the definitions and distinctions between these types of conductors and their roles in electrical systems. Understanding these differences is crucial for proper overcurrent protection and compliance with electrical codes. Secondary conductors, as the name suggests, are conductors connected to the secondary side of a transformer. Their primary function is to carry electrical power from the transformer's secondary winding to the load it serves. These conductors are part of the derived system because the transformer isolates and transforms the voltage from the primary system to the required voltage for the load. The National Electrical Code, or NEC, provides guidelines for sizing and protecting these conductors based on the transformer's output voltage and current rating, as well as the characteristics of the load they serve. Service conductors, on the other hand, are the conductors that bring power from the utilities distribution system to the service equipment of a building or structure. These conductors typically originate at the utilities transformer and terminate at the main disconnect or service panel. Service conductors are subject to specific requirements in the NEC, including minimum size, ampacity, and overcurrent protection to ensure the safety and reliability of the electrical system. Tap conductors are a specific type of conductor that branches off from a main feeder or busbar to supply power to individual loads or equipment. Tap conductors are typically shorter in length and smaller in size than the main feeder conductors. The NEC allows for the use of tap conductors under certain conditions, such as when the tap conductors are protected by overcurrent devices sized appropriately for their ampacity and length, and when the tap conductors terminate in a single overcurrent device that does not exceed their ampacity. The rules governing tap conductors are designed to prevent overheating and potential fire hazards. In the context of a transformer, it is important to distinguish between secondary conductors and tap conductors. The conductors that leave the secondary side of the transformer and supply power to the main load are considered secondary conductors, not tap conductors. Tap conductors, in contrast, would be conductors that branch off from the secondary conductors to supply power to specific, smaller loads. To illustrate this distinction, consider a scenario where a transformer supplies power to a panel board. The conductors that connect the transformer's secondary terminals to the main lugs of the panel board are secondary conductors. However, if a separate set of conductors is run from the panel board to a specific piece of equipment, such as a motor or a lighting fixture, those conductors would be considered tap conductors. Understanding the difference between secondary conductors and tap conductors is critical for proper overcurrent protection. Secondary conductors must be protected by overcurrent devices sized appropriately for the transformer's output voltage and current rating, as well as the ampacity of the conductors. Tap conductors, on the other hand, must be protected by overcurrent devices that are sized appropriately for their ampacity and length, and that comply with the requirements of the NEC. Improper overcurrent protection can lead to overheating, equipment damage, and potentially fire hazards. The NEC provides specific rules for overcurrent protection of both secondary conductors and tap conductors. For example, NEC Section 450.3 covers the overcurrent protection of transformers, while NEC Section 240.21 covers the overcurrent protection of tap conductors. It is essential to consult these sections of the NEC to ensure that the overcurrent protection is properly sized and installed. In addition to overcurrent protection, it is also important to consider the ampacity of the conductors. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. The NEC provides tables that list the ampacities of different types of conductors based on their size, insulation type, and installation conditions. When sizing conductors, it is essential to select conductors with an ampacity that is equal to or greater than the calculated load current. This will ensure that the conductors do not overheat and that the electrical system operates safely and reliably. Another important consideration is the voltage drop in the conductors. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors with a large enough size and to keep the length of the conductors as short as possible. In summary, the conductors that leave the secondary side of a transformer are considered secondary conductors or service conductors, not tap conductors. Secondary conductors are used to supply power to the main load, while tap conductors are used to supply power to specific smaller loads. Proper overcurrent protection and conductor sizing are essential for the safe and reliable operation of electrical systems. The NEC provides specific rules and guidelines for overcurrent protection, conductor ampacity, and voltage drop. It is important to consult these rules and guidelines to ensure that the electrical system complies with the NEC and that it operates safely and reliably. Consider a practical example to solidify the understanding. Imagine a 75 kV transformer stepping down voltage from 480 volts to 208 volts/120 volts for a commercial building. The conductors running from the transformer's secondary terminals to the main distribution panel are the secondary conductors. To determine the appropriate size and overcurrent protection for these conductors, you would first calculate the transformer's secondary current. The formula for calculating the secondary current is kilovolt amperes times 1000 divided by the secondary voltage. In this case, it would be 75 kilovolt amperes times 1000 divided by 208 volts, which equals approximately 360.58 amps. According to NEC Table 310.16, you would need to select conductors with an ampacity of at least 360.58 amps. For example, you could use 3 sets of 300 kc copper conductors with THHN insulation, which have an ampacity of 285 amps per conductor. Since there are 3 sets, the total ampacity would be 855 amps, which is more than sufficient to carry the calculated load current. Next, you would need to select an overcurrent device to protect the secondary conductors. According to NEC Section 450.3, the overcurrent protection for a transformer secondary must be sized no greater than 125% of the transformer's secondary current. In this case, 125% of 360.58 amps is 450.73 amps. Therefore, you could use a 450 amp circuit breaker to protect the secondary conductors. Now, let's say that you want to install a separate circuit to power a specific piece of equipment, such as a 20 horsepower motor. The conductors running from the main distribution panel to the motor would be considered tap conductors. To determine the appropriate size and overcurrent protection for these tap conductors, you would need to follow the rules outlined in NEC Section 240.21. These rules specify the minimum length and ampacity requirements for tap conductors, as well as the maximum size of the overcurrent device that can protect them. For example, if the tap conductors are less than 10 feet long and have an ampacity of at least 1/3 of the overcurrent device protecting the feeder, then you can use a single overcurrent device to protect the tap conductors. In this case, you would need to select conductors with an ampacity of at least 1/3 of the 450 amp circuit breaker, which is 150 amps. You could use 1/0 American wire gauge copper conductors with THHN insulation, which have an ampacity of 150 amps. You would also need to install an overcurrent device at the end of the tap conductors to protect the motor. The size of this overcurrent device would depend on the motor's full load current rating and the type of motor. By following these steps and consulting the NEC, you can ensure that the secondary conductors and tap conductors are properly sized and protected, and that the electrical system operates safely and reliably. Remember to always consult with a qualified electrician or electrical engineer to ensure that the electrical system complies with all applicable codes and regulations. Furthermore, consider the impact of harmonic currents on transformer secondary conductors. Nonlinear loads, such as electronic devices and variable frequency drives, can generate harmonic currents that flow back into the electrical system. These harmonic currents can overload the transformer and the secondary conductors, leading to overheating and equipment damage. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to oversize the transformer and the secondary conductors. The NEC provides guidelines for dealing with harmonic currents in electrical systems. Another factor to consider is the type of grounding system used. The grounding system provides a low impedance path for fault currents to flow back to the source, which helps to protect equipment and personnel from electrical shock. There are several different types of grounding systems, including grounded, ungrounded, and impedance-grounded systems. The type of grounding system used can affect the size and type of conductors required for the secondary circuit. The NEC provides specific requirements for grounding electrical systems. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to consult with the local authorities to ensure that the electrical system complies with all applicable codes and regulations. Finally, remember that electrical work can be dangerous. Always take appropriate safety precautions when working with electricity. Wear appropriate personal protective equipment, such as gloves and safety glasses, and always de-energize the circuit before working on it. If you are not qualified to perform electrical work, hire a qualified electrician to do the work for you. Electrical safety is paramount. Ignoring safety precautions can lead to serious injury or even death. Always double-check your work and ensure that all connections are tight and secure. By following these guidelines and taking appropriate safety precautions, you can ensure that the electrical system operates safely and reliably. The knowledge of secondary conductors and tap conductors also applies to renewable energy systems such as solar photovoltaic systems. Solar inverters convert direct current electricity generated by solar panels into alternating current electricity that can be used to power homes and businesses. The conductors that connect the solar inverter to the main electrical panel are considered secondary conductors. The same principles of overcurrent protection, conductor sizing, and grounding apply to solar photovoltaic systems as to other electrical systems. It is important to consult with a qualified solar installer to ensure that the solar photovoltaic system complies with all applicable codes and regulations. Similarly, the principles discussed also relate to battery energy storage systems. Battery energy storage systems store electrical energy for later use. The conductors that connect the battery energy storage system to the electrical panel are considered secondary conductors. The same principles of overcurrent protection, conductor sizing, and grounding apply to battery energy storage systems as to other electrical systems. It is essential to consult with a qualified installer to ensure that the battery energy storage system complies with all applicable codes and regulations. Understanding the nuances of conductor types and their applications is crucial for anyone involved in electrical design, installation, and maintenance. A thorough understanding of the NEC and other applicable codes and regulations is essential for ensuring the safety and reliability of electrical systems. Continuous learning and professional development are vital for staying up to date with the latest technologies and best practices in the electrical industry. This includes attending training courses, reading industry publications, and participating in professional organizations. Moreover, effective communication and collaboration are essential for successful electrical projects. This includes communicating clearly with clients, architects, engineers, and other stakeholders, and collaborating effectively with other members of the project team. In conclusion, the conductors that leave the secondary side of a transformer are considered secondary conductors or service conductors because they receive their supply from a derived system. They are not typically considered tap conductors unless they branch off from the secondary conductors to supply power to specific, smaller loads. Proper overcurrent protection, conductor sizing, and grounding are essential for the safe and reliable operation of electrical systems. Consulting with qualified professionals and adhering to all applicable codes and regulations are crucial for ensuring the safety and compliance of electrical installations. The NEC serves as the cornerstone for safe electrical practices, providing detailed guidelines on conductor selection, overcurrent protection, and grounding. Staying informed about updates and revisions to the NEC is vital for all electrical professionals.